This video complements our IROS 2019 paper submission, where we present a method for motion planning in unstructured environments. By formulating a nonlinear model predictive contouring control problem, we avoid collisions with the static environment and we anticipate on predicted behavior of dynamic obstacles. Our method combines both planning and control in one module to generate kinematically feasible local trajectories. We provide real experiments and a comparison to state-of-the-art methods. Segments of the reference path are parameterized by the traveled distance along the path, omitting the need of a reference trajectory. We adopt the path progress as a state in the motion model, such that we can evaluate the approximated tracking cost over the prediction horizon. Progress is ensured by a cost term devoted to following a desired reference velocity. In order to avoid collision with the static environment, a polygon convex region in free space is computed for each prediction step. Each ellipsoid dynamic obstacle is enlarged such that we can prove that our collision constraint with respect to the vehicle representing disks entirely bounds the collision space. Additional clearance from moving obstacles is created with a repulsive cost term. Our method is fully implemented on board of a mobile robot, including localization and perception based on sensor data, and runs in real time thanks to its lightweight implementation. In this experiment, we show how we avoid collision with the static environment in an updated occupancy grid map. The yellow area in the visualization represents the polygon convex region, being the feasible set of solutions for the optimal control problem. The feasible region is affected by the doors that have to be opened and the obstacle on the reference path. We compare static collision avoidance to the ROS navigation stack, where the dynamic window approach is used for local motion planning. In this particular scenario, the dynamic window approach is not able to find a solution through the narrow static environment to keep following the reference path, while our method is able to deviate from the reference path to keep traversing the environment. Using a pedestrian simulator, we inspect the behavioral difference between our approach and two other state-of-the-art methods. We can clearly see that our method anticipates on future positions of dynamic obstacles, whereas the other methods are too reactive and do not act on the future state of the environment. In a closed dynamic environment, we tested planning performance of our method following a predefined path. The green circles in the visualization represent the interacting pedestrian, which are being tracked by a motion capture system. Using a linear velocity prediction, we can see that the planner is able to anticipate on the dynamic behavior and create smooth avoiding maneuvers. This experiment shows performance of the planner in a full navigation stack, completely relying on onboard sensor data. The robot traverses a corridor and a smooth avoidance maneuver is performed. Although the tracker detects the second pedestrian rather late, the planner is able to react fast enough to avoid collision. Compared to the dynamic window approach that is using a replanning technique in an updated static environment, our planner is able to come up with a motion plan to efficiently overtake a pedestrian that is walking through the corridor. Finally, we show that our method is applicable to different vehicles, such as cars, using a kinematic bicycle model. We simulate a scenario where the car has to overtake a cyclist to maintain its desired velocity, while simultaneously avoiding collision with a crossing pedestrian.